organizers to thank, so thank you, the audience. So what I'm going to talk about is joint work with Alexei Bonda, and it's about exact categories. So yeah, I'm going to tell you a little bit about their structure and some interesting observations that we made. So it's not directly related to mirror symmetry yet, but I think it's a very nice story to tell. So let me start with a definition. So what is an exact category? It's an additive category with short exact sequences. So an exact category E is an additive category with a class of kernel-co-kernel sequences so I have X goes to Y goes to Z. So I mean X is the kernel of D, or I is the kernel of D, and D is the co-kernel of I. So they are called conflations. And the first arrow is usually called an inflation, and the second arrow is a deflation. Which I must say is a very unfortunate choice of names, because whenever you try to Google, you always get all these inflation rates and deflation rates. And Googling anything about exact categories, you need to be more specific. So it's the definition. I'm just writing down the definition. So it's an additive category with a class of kernel-co-kernel sequences. And now, so they are called conflations. And now they need to satisfy some axioms. So first of all, the identity needs to...
Exact sequence of category.
No.
Exact sequence of Jacob-Brits, but exact sequence of category is something.
I'm not saying this is a kernel-co-kernel sequences of objects of E.
An object of E, yes. For any object, we have this sequence.
No. I have sequence. I have sequences.
Okay.
And now I tell you what axioms they satisfy. So first of all, for any object of E, when I go 0, then to my object, and then to identity, this is a conflation. The second axiom tells that when you compose two deflations, it's still a deflation. And then the last two axioms tell you that you can do what you are very well used to doing in abelian categories, meaning you can compose. So you can think of it as X1s, and you can compose X1s with morphisms in your category. So to be precise, maybe let me draw it here. So when you have a short exact sequence, a class in X1, and you have a morphism, now I never know where to do it, right? So when I have a morphism, I can take a pullback. If I am in abelian category, I can take a pullback, and this is still a short exact sequence. So now my category is only additive. It doesn't need to have pullbacks. So the axiom says that this pullback always exists. So the axiom says that the pullback of a deflation along arbitrary morphism exists and is again a deflation, meaning if this was a short exact sequence, then this is also a short exact sequence, and the other way around, right? So if I have a map here, then I can take a push out, and this will also be a short exact sequence. So a push out of an inflation along arbitrary morphism exists and is a deflation, is an inflation. So these are the axioms of an exact category. So what about examples? So examples, first of all, I can take an additive category and I can take conflations to be just short split sequences. Split. Or I can take A to be abelian and conflations to be all short exact sequences. Or I can take some fully exact subcategory of those. So a fully exact subcategory of those, meaning a full subcategory. So what fully exact means, it's a full subcategory closed under extensions. So when I have a conflation in A, A1, A2, A is any exact category, but you can think of it just about being abelian. I will tell you why in just a second. So I mean to say, if this guy is in X and this object is in X, then the category is closed under extensions if this one is also in X. And what Gabriel-Quillen theorem says is that these are all examples, meaning any exact category is a fully exact subcategory of an abelian one. So the way you construct this fully exact subcategory, you just, this abelian category of an abelian one, you just take sheaves on your exact category. You just take left exact functors. But to be honest, this abelian category that your exact category lives in, it doesn't tell you much because it's much bigger. So for example, to determine whether an exact category has kernels, it's not an easy question. Like even you know that it's not close under kernels in this big abelian category, it still doesn't mean that it does not have kernels on its own. Okay, so what I want to do, I want to mimic somehow the theory of abelian and triangulated categories in the words of exact categories. So when you have an abelian category and you want to understand it, one way to do it is to think about a torsion pair. So you can think about torsion pairs, or if you would view this exact category as a triangulated category somehow, then you can try to think about semi-orthogonal decompositions. So let me make this precise. So I consider some fully exact subcategory of an exact category. And if I want to view it as a torsion pair, I should consider the perpendicular, the orthogonal category, which I will denote this way. So these are all objects E in E, such that there are no homes from my subcategory to the object. Or I can consider the other one, so the other orthogonal. So these are all E in E, such that there are no homes from E to X. So this one is right orthogonal. This one is left orthogonal. And if I want to think of it somehow in a triangulated way, I can ask for a complete orthogonality, but for an exact category, I only have homes and X1s. So I can think of X perpendicular, which are all objects such that there are no morphisms from my subcategory X to E, and there are no X1s from subcategory X to E. So this will be the right perpendicular. Well, or dually, I can put the perpendicular on the other side. So I have no homes from E to X, and I have no X1 from E to X. So this will be the left perpendicular. And I told you that we can think of building blocks as some kind of torsion pairs. So what is a torsion pair? Well, so E, this is just a notation, TF is a torsion pair. Well, if, first of all, there are no morphisms from T to F, and then any object E in E, there exists a conflation with an object in T and then an object in F. So it's like for abelian categories and a torsion pair. So I will say that a category is weakly left or right admissible if it fits into a torsion pair. So X in E is weakly right admissible if the embedding factor from X to E has right adjoint I upper shriek, and for any E in E, the co-unit, so I go from I low star I upper shriek of E to E, is an inflation. And then it is weakly left admissible if the embedding factor has left adjoint I upper star, and the unit is a deflation. And then an easy lemma says that Ex is weakly right admissible if and only if there is a torsion pair X and then X orthogonal. So this is one way to decompose exact categories into smaller ones, but it seems that it's not the most powerful one. So we really would like to view these exact categories more of like triangulated ones. So we would like to have this stronger orthogonality, not only home orthogonality, but also X1 orthogonality. So I will say that what is a perpendicular torsion pair? A perpendicular torsion pair, TF, so it's a torsion pair such that there is also no X1 from T to F. So it's more like a semi-orthogonal decomposition. I mean, you not only have home vanishing, but also the X groups that you can make sense of vanish. And then, so this was a weakly right admissible. So I will make a slightly different definition of admissible. So X in E is a subcategory, is right admissible. So this is a definition. If there exists a perpendicular torsion pair and then it's left admissible if it's on the other side. So I can put it like this. But now it turns out, so theorem says that if I have a category which is weakly right admissible, meaning there exists an adjoint functor, then it is admissible. So I assume it's weakly admissible, so it's admissible, it's right admissible. If and only if this functor adjoint is exact, meaning it maps I upper shriek maps conflations to conflations. Okay. So why do we like this stronger? Why do we like this stronger definition more? Well, because it gives us a semi-orthogonal decomposition on the derived category. So when a category E is exact and weakly idempotent split, which means that for any morphism, any retraction, meaning a morphism which has a section, so there exists section from E prime to E such that Rs is the identity on E prime. So any such retraction should have a kernel. So this is a definition of a weakly idempotent split category. Okay, so this is Thomasson who described it. So then we can form the derived category of E. So we define dB of E as the quotient of the homotopy category of complexes over E by acyclic complexes. So this condition is required for this subcategory to be closed under direct summation. So then you can really take the quotient. So this is the definition of a derived category. And so now one easy lemma is that if we have a perpendicular torsion pair, then E is weakly idempotent split if and only if T and F are. And then, moreover, when we have this perpendicular torsion pair, it gives us a semi-orthogonal decomposition on the bounded derived category. So the theorem says, let's from F to E be a left admissible subcategory, meaning it's a part of a perpendicular torsion pair. So I assume that everything is weakly idempotent split. So then this dB of F is left admissible subcategory of dB of E, and we have a semi-orthogonal decomposition, so this dB of E is dB of F, dB of F perpendicular. Meaning, as soon as we assume that there is just no x1 vanishing, it turns out that also all higher x vanish. I mean, that they are completely orthogonal. I mean, they are orthogonal on the level of derived categories. So here is a very unfortunate convention. So usually when you write, when we write torsion pairs, there are no morphisms from right to left, from left to right. And when we write semi-orthogonal decompositions, there are no morphisms from right to left. That's why they changed that's why the order changed. Okay, so now I would like to say a little bit about, so we assume that this is somehow a good way to build our exact categories from smaller pieces. So, but now we would like to consider some longer decomposition. So to do it, it doesn't have to be linear. So we say that there is some poset. So lambda is a finite poset. And we want to make a filtration on our category which would be somehow labeled by this poset. So more precisely, I should consider the lattice of lower ideals in lambda. So what is a lower ideal? So I in lambda is a lower ideal if for any I in lambda and any j which is less than I, j is also in lambda. And then, so this is a distributive lattice. You can intersect and take unions, and it still will be a lower ideal. And Birkhoff theorem says that any finite distributive lattice is of this form. So what is a filtration? So a right admissible I of lambda filtration on category E is some Ti inside E for any I in I lambda such that, well, first of all, we want this filtration to be everything. So we want that the empty ideal is just 0 and the full ideal is the whole category. Then we want that this T of I is always right admissible. And then what we want is that T, that it behaves well with respect to intersections, and that it behaves well with respect to unions. So when I take union, I should in fact take the perpendicular and intersect there. Okay. And then there is one technical condition which is very useful. So the filtration is strict if, let me first do it on a picture. So assume I have some category which corresponds to I, and I have some category which corresponds to J, then this will of course be the intersection. But the question is, what is this guy? So I can either take Tj and somehow remove this part, or I can take the category which corresponds to the union and remove all this Ti. And what we want that these are the same. So I want to say that when I take Tj and I intersect it with Tij perpendicular, it should be the same subcategory as Ti, the sum of j intersected with Ti perpendicular. So the problem here, why do I need to say it this way, is that we don't really have quotients of exact categories. At least we didn't manage to construct them in a nice way yet. So what is the theorem? The theorem says that if I have this Ti inside E, it's a strict right admissible filtration. Then it's also a strict right admissible filtration on triangulated categories T. Right admissible filtration. And this is something we know very well. So a strict right admissible filtration on a triangulated category is a semi-orthogonal decomposition. So yeah, let me just make it let me assume that somehow my poset is like this, because that's enough. So I would have the category corresponding to the minimal element. Now I might confuse, it should be on the right. Okay, so it should be on the right. Then I take the category which corresponds to this lower ideal, so it will be T2, 1, but I need to mod out the dB of T1, and then I take dB of T31 and I mod out dB of T1. So somehow I take this smallest pieces corresponding to this filtration. So this is a semi-orthogonal decomposition, and the strictness means, when you translate it to the, I mean, you can define it this way, but when you have triangulated categories, you have quotients, and then the strictness means that there are no homes from this category to this category and vice versa. So these two categories are completely orthogonal. So this is how you can formulate strictness when you think about triangulated categories. So this is the story, and now if you want to study, we thought that if we study exact categories, we can start from the simplest class. And what would be the simplest class? It would be built from the easiest blocks. And the easiest additive category is the category of vector spaces. So somehow we consider exact categories whose derived categories have full exceptional collection. If you look on this theorem, if you build your exact category from just vector spaces, then the derived category will have a full exceptional collection. So a definition is, so a K-linear home and X1 finite exact category is thin. If it has a filtration, right admissible filtration, so I start from T0, then I have some T1, and I end with Tn. Well, let me call them graded factors. Meaning I take Ti and intersect with perpendicular to Ti minus 1. So I want that this guy is just finite dimensional K vector spaces for any I. So this is like this exact category is built from the smallest, the easiest blocks. And it turns out that they are related to highest weight categories. So what I want to finish the talk with is to explain you how from these thin categories you can construct highest weight categories. So I will say what the highest weight category is in a second. But now let me just say what is so when I start from a thin category, there will be some canonical poset which will be assigned to it. So I have this is a subcategory of my exact category, right? So let me just denote it by EI. It's equivalent to vector spaces. So there is an object Now it's a non-curly EI, which corresponds to one-dimensional vector space there. And so then this E1 to En, these are all, this is the set of isomorphism classes of irreducible objects in E, meaning they are not extensions of any other objects. And we can introduce a partial order on this set. So we just say that if EI is not in EJ perpendicular, meaning there is a morphism from EJ to EI or an X1 from EJ to EI, then I is less than J. So we take the smallest partial order on lambda, which satisfies this property. So take the smallest. Partial order, which satisfies. And then, well, what you can do, you can define for any lower ideal in lambda, you can look at the category which I will denote this way, lambda in I. So these are the full subcategory of objects which have a filtration, meaning a sequence of conflations with graded factors EI, E lambda, okay, I should say it this way. EI, I is in I, so it should be EI, I is in my lower ideal. So somehow I take the extension closure of this object, and then an easy observation is that I will get a right admissible filtration. I mean, it's a number of, I mean, I assume everything is finite, so it's just a number of indecomposable objects. It's the length of the poset. In what sense does it mean?
I mean, if you have another filtration,
yes, it also needs to have the length n, because well, because the length n tells you how many irreducible objects you have up to isomorphism. So this is invariant of the category. And so, of course, this filtration that I started from is not unique, but what you get, so I define this Ti as this subcategory F of EI, right? I is in the ideal. So this would be a right admissible filtration. Strict filtration on E. And any filtration of length n, it would somehow be, so I have some partial order on my elements from 1 to n, and any full order which you would choose, which is compatible with this canonical order lambda, it will be the filtration that the F infiltration. Okay, so now I want to tell you a little bit how from an exact category one can construct an abelian one. So as I said in the beginning, an abelian category is an example of exact category, but it has more structure. So for example, we can define, say, a right or left exact functor from an exact category to an abelian one. So if so let me say that E is exact and A is abelian. So a functor F from E to A is right exact if for any conflation where I have an exact sequence, f of x, f of y, f of z, 0 is exact in A. And then I can also say when it is left exact, well, I put the 0 on the other side. F of x, f of y, f of z. And then, of course, you can say that it's exact if you put 0 on both sides, and it agrees with what I said before, what is an exact functor between exact categories, that it maps conflations to conflations, and in this setting, it will map conflations to short exact sequences in A. And the question which we asked is, maybe we have some universal category which, with respect to right and left exact functors, to abelian categories, or in general, exact functors. So this is the envelope. So the right abelian envelope of an exact category E is an abelian category A R of E together with a right exact functor IR from E such that for any abelian category B, so I can consider the category of right exact functors from my envelope to B. So the objects are the right exact functors, the morphisms are natural transformations, and then I can compose them with my functor IR. I will get the right exact functor from E to B, and I want this to be an equivalence. So in other words, whenever I have a right exact functor from my category E, then I can more or less uniquely extend it to a right exact functor from the envelope. So this is right exact, and then I have my IR to the envelope, and this one is unique up to isomorphism. So, of course, you can analogously define what would be the left abelian envelope So it has the universal property with respect to left exact functors. And you can just look at exact abelian envelope, which would be the universal property with respect to exact functors into abelian categories. So the only thing which has been studied before is this one. And so there is a master thesis of a student from Stuttgart, Nico Stein, from 2014, in which he describes this exact envelope. So he gives a construction of this envelope, and so this is E, exact envelope. And how do we do it? Well, first we look at the category which was considered by Adelman in the 70s for any exact, any additive category. So here the objects are just sequences of objects in E. The composition does not need to be 0. And the morphisms, so when I have another one, E0 prime, B1, E1 prime, B2, E2 prime. So I have here some F0, F1, F2, and they are equivalent. So the morphisms are these triples, F0, F1, F2, which make it commutative up to equivalence. So F0, F1, F2 is equivalent to G0, G1, G2. And now this is a little bit of surprise. I mean, you need to have homotopy, but it needs to be a homotopy only in the middle. So you need to, so this is if and only if there exists this U and V such that G1 minus F1 is A1U plus V B2. So you don't want this homotopy to be a homotopy on the outside, only in the middle. And so this is somehow the universal abelian category of an additive category. So it was constructed by Adelman in the 70s. And then what Nico proved, he proved that we can take a Serre subcategory, mod it out, and then we will get the exact envelope. So A exact of E is this Adelman category of E when you mod out S. So S is the Serre subcategory whose objects are. So I have a conflation. X, Y, Z is a conflation. And every conflation gives me 3 objects of S. So first of all, I have 0, X, Y in S. Then I have X, Y, Z in S. And then I have Y, Z, 0 in S. So when I mod out this Serre subcategory, I will get this exact abelian envelope. So unfortunately, we don't have a general construction of a right and left abelian envelope, but there is some statement in Kashiwara-Shapira book which helps us to construct some examples. So the theorem of Kashiwara-Shapira says that if you have a subcategory of an abelian category, which is closed under extensions and under kernels of epimorphisms, and if any object is a quotient of an object of an exact category, then it will be an envelope. So the theorem E in A is a full subcategory closed under extensions and kernels of epimorphisms. And then, if every object A in A is a quotient of some E in E, then A is the right abelian envelope of E, which gives you the first geometric example. Let us consider a scheme with resolution property. It means that every coherent sheaf is a quotient of a locally free sheaf. So then this theorem tells you that the category of coherent sheaves of X is the right abelian envelope of the category of locally free sheaves on X. So this is one example of a right abelian envelope. And the other way to construct right abelian envelopes is, well, I can look at a projective object in E. So this would be a projectively generating subcategory, meaning every P in P is projective. So x1 from P is 0, and every object of E, there exists a conflation or deflation from an object of P. And then if the category P has weak kernels, so P has weak kernels, so what it means that any morphism X to Y, there exists some morphism G such that the composition is 0, and whenever there is a map such that the composition is 0, there exists a lift, but it does not have to be unique. So this is the definition of a weak kernel. So why do we need it? Because Freyt proved that category has weak kernels if and only if the category of finitely presented contravariant functors is abelian. So this is in left exact from P op to ab. So these are functors which have a presentation of with two representable functors. The quotient of it's a co-kernel of representable functors. So this category is abelian if and only if P has weak kernels. So this is Freyt. And then what you can say, well, if you have an exact category which has a projectively generating subcategory with weak kernels, then this finitely presented functors will also be an envelope for your exact category. So observation. So P in E is finite, is a projectively generating subcategory with weak kernels. Then this Fp of E is the right abelian envelope of E. And this weak kernels is somehow that it's about being coherent, right? I mean, you want that finitely presented modules are abelian categories, so you want the category to be coherent. So if the category that you started from, say, has finitely dimensional homes, then, and this is just a subcategory which is generated by some finite number of objects, then it will always have weak kernels. And so this observation allows us to construct right and left abelian envelopes for thin categories. So now if E is thin, then it has enough projectives and injectives you just construct them inductively. So I had these objects E1 to En. So this guy is already projective because there was no home and no x1 to anything further. So this guy is projective. And then if I have some projective objects here, say Qi, then what I do, I take the universal extension. So this would be E1 tensor with x1 from Qi to E1 d1. So this is the universal extension, and then this guy is projective also. And dually, you can construct injective object. And then the theorem says that when I take the right abelian envelope of E and I take the opposite poset, or when I take the left exact category of E and I take the canonical poset for E, this will be highest weight categories. So first of all, they exist, and then they are highest weight categories. Moreover, they are Ringel dual to each other. So what is a highest weight category? So it's an abelian category which has some special objects. So they are so-called standard objects, and you require that projective objects have filtrations with standard, and standard objects have filtrations with simples, and there need to be this poset has to be included in the picture. So lambda is a finite poset, and A is abelian. So I assume that this lambda, so A lambda is highest weight if lambda is a poset on isomorphism classes of simple objects in A. So I have some L lambda for any lambda in lambda. So this is simple. And there exists delta lambda, so-called standard modules, standard object, such that, first of all, every delta lambda has a map on the simple object with the same index. and the kernel has a filtration with simple objects which are strictly smaller than lambda, and then projective cover of simple, this is a projective cover of L lambda, it has a map to the standard one, and the kernel has a filtration with standard which are now strictly greater than lambda. And dually, there exists some co-standard which behave well with respect to injective modules. So L lambda, nabla lambda, and then there is this L mu less than lambda, and nabla lambda is a submodule if in injective hull of simple, and the quotient again has a filtration with costandard with which are strictly greater than lambda. So this is equivalent to this. You require one, you get the other. And it turns out, well, one easy thing to check is that every, so when I take the subcategory of objects which just have this standard filtration, then this is thin. And here this category is also thin. And my abelian category is the right abelian envelope of this one, and is the left abelian envelope of this one. And then, so there is a duality between highest weight categories, which was constructed by Ringel, and it more or less says this. This is a thin category. I told you that a thin category has a projective generator. I told you explicitly how to construct it. So what Ringel said, he said, let's take the projective generator for this category. And then modules over its endomorphism algebra will again be a highest weight category, and this is the Ringel dual. So this point of view allows us to view this left and right envelopes as some incarnation of Ringel duality. And one last thing I want to say is that I constructed this cover, this abelian envelopes from projective objects. And because of this, I have an equivalence of the bounded derived category of my thin category is equivalent to the bounded derived category of the right envelope, and is equivalent to the bounded derived category of the left envelope, because the left envelope I construct from injectives. And then it turns out, so these two categories, they have T structures, they are derived categories of abelian ones, and E is just the intersection of kernels. So, of course, now there's many questions, like how general is this fact that when the envelopes exist, whether the exact category would always be the intersection of right and left envelope. Yeah, so this is all work in progress to answer all the natural questions. So that's all I wanted to say. Thank you.